Okay, guys, now we are going to talk about the triple integrals in Cartesian coordinate system. Here they say rectangular means Cartesian. Uh, when we are talking about the triple integrals, it means we want to define integral for a function of three independent variables, something like this: f of x, y, z, three independent variables. So we know that the domain of this function is a subset of three-dimensional space, right? And you suppose that this function f on a bounded region like D in three-dimensional space is defined and is continuous, okay? Just like double integral, to define the integral for f, we partition this region D by some line parallel to x-axis, y-axis, and z-axis. When we partition this region D, inside the region D, you will see a finite number of small boxes, something like this. You can see here. And of course, here delta V, okay, I think better we denote this V with capital V, but here they denote it by a small v, but it doesn't matter. So delta V is the volume of these small boxes, a small box, which is the product of delta X, delta Y, and delta Z, as you can see here. Now, inside each small box, we choose any arbitrary point, like xk, yk, zk. And we form this sum, which is the Riemann sum, right? Sigma f of xk, yk, zk, it means the value of function at this point, times delta vk, which is the volume of this, the kth small box. And you can see delta vk is the product of these three elements. So now we take limit of this Riemann sum when n approaches infinity. When n approaches infinity, this is equivalent to saying that the volume of the largest box approaches zero. But okay, just focus here. When we take limit when n approaches infinity, we can show that the limit of this Riemann sum exists and is defined to be the triple integral of f on D, which is denoted like this: triple integral of f dv on D, like this. And this dv is dx, dy, dz, or later we will talk about the order of the integration. Now, before we check some example, look at these properties of triple integrals, which are very similar to the properties that we have for single integrals and double integrals. Okay, the first one, the integral of kf. K is a scalar, okay, a real scalar. This k can move out, equals k times the integral of f. Similarly, the integral of f plus or minus g equals the integral of f plus or minus the integral of g. It means the integral of sum equals the sums of integrals, the sum of integrals. This one is interesting. Number 3. If f on D is positive or non-negative, it means the values of f on D are non-negative, then the integral of f dv on D will be non-negative. This is very quite easy. It's quite easy to understand, because look at here, the integral of f is defined to be the limit of Riemann sum. So when f on D is positive, so for every point like xk, yk, zk, f here is positive. So f is positive, delta vk's volume of course is positive. So here this sum is positive actually. Sum of the this is the sum of the positive, the values. So this sum is positive, and of course when you take limit, the limit will be positive. So that's the reason. Like this. And property number 4, which can be obtained from number 3. Look at here on region D, bounded region D. The values of f are greater than the values of g. So we can prove using 3 that the integral of f on D is greater than the integral of g on D. Property number 5, look at here. Let's say our region D is a disjoint union of two regions, D1 and D2. When I say disjoint union, it means D1 and D2 does not overlap unless except at the border. Okay, so D1 is the disjoint union of D1 and D2, and D1 and D2 does not overlap except at the border. So the integral of f on D equals integral of f on D1 plus integral of f on D2. But let me explain you. This property is true for any region D of any shape. Let me show you. It means D doesn't have to be of rectangular shape. This is true for actually, let me show you. Yes, look at here. Let's say our D is, okay, hold on a second. I have to make it bigger for you. Okay, let's say D is of this shape, for example, and D is like a three-dimensional object like this. So let's say this is our D. Okay, this is D1, this is D2, like this. So it means this property number 5 is true for D of any shape. You can see here, not only rectangular. Okay, look at here on the next page. Okay, we already talked about this page, right? Okay, we have a comparison between the double integrals and triple integrals. Of course, the difference between these two is obvious. When we are talking about the double integral, it means we are talking about the integral of a function of two independent variables on a bounded region in two-dimensional space. When we are talking about triple integrals, we are talking about the integral of a function of three independent variables on a bounded region in three-dimensional space. So they are completely different things, and the difference is obvious. We don't need to talk about this much. So let's move on the next page. Okay. Now listen very carefully. We are going to talk about how to find limits for integration in triple integrals. Look at here. If you remember, in double integrals, we only have two orders, dx, dy, dy, dx. But for triple integrals, totally we have 6 orders. Be very careful. Totally we have 6 orders. For example, dz, dy, dx, dx, dy, dz, dz, dx, dy. So totally we can have 6 orders. But here in our work, and of course this order of integration depends on how we describe the region D. But here in our work, in this course for you, usually we set up the integral in this order: dz, dy, dx. But again, I remind you, that's not the only the case. Okay, you usually try to set up in this order. Okay, if we set up in this order dz, dy, dx, we describe the region D like this. Look at here. You suppose that this is our region D. Okay, from the below is bounded by a surface, and the equation of this surface is z equals f1 of xy, and from above is bounded by another surface, like this is upper surface, this is lower surface, this is upper surface, with the equation z equals f2 of x and y. So we can say, look, you just imagine that you are flying inside the region D. So do you agree with me? Z is from the lower surface to upper surface. It means Z is from f1 of x to f2 of x. And then look at the image or the projection of region D onto xy plane. Okay, onto xy plane. When you get the image of region D onto xy plane, the image will be a region in two-dimensional space in xy plane. Now you can describe this region in two-dimensional space in the form of case 1 or case 2. Do you remember from double integral? So here you can see. Now, to describe the region, the image of region D onto xy plane, to find the limits for y and x, you can see it. We can say y is from g1 of x to g2 of x. Here is lower curve and upper curve for y. So y is from g1 to g2 of x. And then look at here, we can say x is from a to b. So this is how we describe the region D. This is one of the 6 possibilities, okay? So we set up the integral like this. The integral of f, capital F, f of x and y and z, dz, dy, dx. You can see z is from f1 to f2 of x and y. Y is from g1 of x to g2x, and x is from a to b. So now this integral is set up correctly. So just like double integral, first we integrate with respect to z. So whatever is left is a function of x and y. Then we integrate with respect to y. Whatever is left will be a function of x. And finally we take integral with respect to x, and we find the answer. So again, I remind you that we usually set up integral in this order, dz, dy, dx. But there are other possibilities. Totally we have 6 possibilities. Okay, now let's check this example, but there is some point in this example that we have to mention. Do you remember when we want to find the area of some bounded region in two-dimensional space, we calculate the double integral of 1 dA on that region. So now, look at here. Let me show you this slide. If we have a bounded region on three-dimensional space, like D, the volume of D equals integral, the triple integral, 1 dV on D. You can see here if f is 1. It means if you want to find the volume of D, you just take the integral, triple integral 1, or simply dV on D. And why is it like that? So look at here. This integral is defined to be the limit of Riemann sum, right? But here f of x, k, y, k, z, k is 1. So only left sigma, the limit of sigma, delta vk. And delta vk is the product of these 3 elements, which means the volume of each small box. So this sum, it means the sum of all small boxes inside D, right? Which is approximately equal to the volume of region D. But when we take limit, they are going to cover entire region D. So that's why, how to say, the triple integral of 1 dV or 1 dV on D equals the volume of D. So this is how we apply triple integral to find the volume of a bounded region in a three-dimensional space. Okay, now let's back to this example. Look at here, we have a bounded region in three-dimensional space, bounded between these two surfaces. Z equals x squared plus 3y, x squared plus 3y squared, which is this one, and z equals 8 minus x squared minus y squared, which is this one. Okay, you can see between these two, here D is here actually. D is the region between these two. This is from above, this is from below. Okay, so they said upper curve, but actually upper surface, and this one is lower surface. Okay, of course if you partition you will see some curve, but actually this is upper surface and this is lower surface. This is the lower surface for D, this is upper surface for D. So now we want to calculate the volume. So we have to take the triple integral dV on D. So let me do it for you. Okay, so we want to find the volume of D, and the volume of D will be the triple integral dV on D. So now we have to describe the region D and set up the integral and solve it. So look at the image. Okay, to describe the region D, you can see Z is from the lower surface to upper surface. Our lower surface is this, upper surface is this. So you can see Z from lower surface to upper surface. Now, what about limits for y and x? So it means we have to get the image of this region D into xy plane. On the next page, you can see the image of region D onto xy plane is this ellipse. Okay, is this ellipse. But you may wonder why. I mean, how we could get this ellipse. Why the image is this. Okay, let me explain for you. Here you can see actually the intersection of these two surfaces, look at here, lower and upper surface, will be a curve, right? The intersection of these two surfaces will be a curve. That curve will be an ellipse, and the image of that ellipse on the xy plane is this. Okay, now you may wonder how we get the equation of this ellipse. Okay, I'm gonna explain for you. We have to solve this system, okay, because that ellipse is the intersection of these two surfaces. So we have to solve this system. So we put the equation of these two equals each other. So you can see here. So we have x squared plus 3y squared equals 8 minus x squared minus y squared. So let me take these two to the right hand side. So we have x squared plus x squared, we have 2x squared plus 3y squared plus y squared, we have 4y squared equals 8. And now you can see if we divide both sides by 8, if we divide both sides of this equation by 8, then we have x squared divided by 4 plus y squared divided by 2 equals 1. Okay, now this is an ellipse, right? This is the equation of this ellipse. So of course, because this is the image of region D into xy plane, when you want to describe it, this region, you can say y is from the lower surface to upper surface and x is from -2 to 2. But we have to obtain the equation of I said okay, lower curve to upper curve. Sorry, let me correct it. So you have to say y is from lower curve to upper curve, okay, and x is from -2 to 2. Okay, how to obtain the lower equation of lower curve and upper curve? Okay, you can see here using the equation. So here, do you agree with me? I can keep this y squared divided by 2 and take this x squared to the right hand side. So I have 1 minus x squared divided by 4 and then okay, let me take a look at here. Yes, yes, correct. And then we have here, let's take a square root. Okay, let's do like this. Okay, let me erase this one. Okay, so let's continue. Here the right hand side equals 4 here, and 1 times 4, so we have 4 minus x squared. Okay, like this. So we have y squared divided by 2 equals 4 minus x squared divided by 4. Now if we multiply both sides of this equation by 2, so we have I can write here, we have y squared equals 2 times 4 minus x squared divided by 4, and this equals 2 divided by 2, 42. Okay, so we get 4 minus x squared divided by 2. Okay, now look at here, if we take a square root on both sides, okay, the space is not enough. Let's move up here, so I have to erase it. Okay, we have to move up here. Okay, so let's move up here. So we have y squared equals 4 minus x squared divided by 2. Now we take a square root on both sides, so y equals plus minus the root of 4 minus x squared divided, okay, y equals plus minus the square root of 4 minus x squared over 2. You can see here. You can see. So the minus is for this half and plus is for this half. So now we can mention or write the limits for y and x here. So you can see y is from minus to plus and x is from minus 2 to 2. Okay, so here we are going to set up the integral. So since the space is not enough, I have to erase here. Okay, then we continue here. Okay, so this is the description of the region D. You can see. Okay, now let's set up the integral. Okay, triple integral, z from lower surface to upper surface, and then the image of the D on the xy plane will be that ellipse, So y from lower curve to upper curve, x between -2 to 2. Okay, as you can see here. Okay, so sorry. Now, so according to this description, the order of integration will be dz, dy, dx. So first with respect to z, then with respect to y, then with respect to x. So let's do it. Since the space is not enough, I have to erase here first, then we continue. Okay, so the first integral with respect to z. Okay, so this one from -2 to 2, from minus to plus. So the integral of dz with respect to z is z. Okay, z from this to this. So it means the value of z when z equals this minus when z equals this. So since the space is not enough, we have to erase here and move the calculation up here. Okay, you can see, let's move the calculation up here. So when z equals this minus when z equals this. Okay, so you can see this is a double integral. So now we have to calculate this and go ahead the next integral with respect to y, then with respect to x. But we have to erase here to have enough space. Okay, then we continue the calculation here. And you can see here x squared minus x squared, so we have minus 2x squared. Minus y squared minus 3y squared, we have minus 4y squared. So let's do it here. Okay, we are left with this double integral that we have to solve. Since the space is not enough, I want to move it here and we start solving this double integral over this elliptic region. Okay, but of course we are going to see that we have to use substitution. I mean, if we do not use substitution, it might be possible we solve this integral, but will be very difficult, very difficult. So to calculate this double integral on this elliptic region that you can see here, okay, we have to use substitution. So first let me move this one up here. You can see I move this integral up here, but I write 8 minus this 2x squared, I can write it as the root of 2x squared, minus this 4y squared can be written as 2y squared. The reason is to solve this integral, we have to use substitution. Actually, we can use one substitution or substitution one time to calculate it, but it will be difficult for you. So that's why I'm going to use two substitutions. It means we are going to use substitutions twice, step by step, to make the integral easier for you. So that's why first I write it in this way, because like I want to, roughly speaking, you can see, convert this elliptic equation to circular equation. Okay, so let me erase this one first. Okay, now look at here. Before I mentioned about substitution, okay, right, we wrote 2x squared as the root of 2x squared and 4y squared as 2y squared. It's not wrong, but actually we don't have to do this. So let me erase this one and just write it as 2x squared. Okay. It's correct, actually, nothing wrong, but we don't have to do this. Okay, so we have 8 minus 8 minus 2x squared and minus 4y squared. Okay. Now look at our first substitution. Okay. Our first substitution, okay, let me explain you how we choose our substitution. Look at here, this double integral, we have this double integral over this ellipse, right? So we want to use a substitution that convert to this ellipse to a circle, okay? What is the equation of this circle? Do you remember we obtained? Is this. Equation of this circle is x squared over 4 plus y squared over 2 equals 1. But when I said between 0 and 1, it means inside, because the area of the integration is bounded by this ellipse, over ellipse and inside. Okay. So look at here, can I write this x? I can write this one as x divided by 2 squared plus, I can write this one y divided by the root of 2 squared, right? This gives you some idea how to choose your proper substitution. So let me take x over 2 to be u, x over the root of 2 to be v. Equivalently, it means x equals 2u, y equals the root of 2 times v. By this substitution, look at here, your ellipse in xy plane will be converted to a circle in uv plane, right? Because this is u squared plus v squared. So u squared plus v squared equals 1. This is a unit circle in uv plane. It means circle centered at 0 of radius 1. So of course when we say between 0 and 1, it means inside, interior of the circle. So it means when we use this substitution, we get a double integral with respect to u and v over this circle in uv plane. And of course, we do not forget the Jacobian of substitution. You can see the derivative of x with respect to u, 2 with respect to v, 0, derivative of y with respect to u, 0 with respect to v, the root of 2. So the Jacobian will be 2 times the root of 2. Now we have to put it here. Okay, so we have to put it here, and x, y, Jacobian, and the area of integration in uv plane will be, how to say, the unit circle that you can. Okay, let me erase here and then we move up here. Okay, so you can see here, so this integral with respect to u and v, 8 minus x is 2u, y is the root of 2 times v, and we calculate the absolute value of Jacobian, this one, which is 2 times the root of 2. And look at the region. So this elliptic region under this substitution will be converted to a circular region into uv plane. It means this region G, let's say. So it means the integral with respect to v and u and v, or v and u, will be over this circular region, which is the unit circle. U squared plus v squared equals 1. So v squared equals 1 minus u squared. So v equals plus minus the root of 1 minus u squared. Plus is for this upper semicircle, minus is for this lower semicircle. So we set up the, so this is the description of region G. So here you can see v is from lower semicircle to upper semicircle, u is from minus 1 to 1. Okay, so now let's put the Jacobian here. I'm going to erase here, then we move up here to calculate the integral. Okay, you can see here integral from minus 1 to 1, from minus root to this one. 8 minus, this becomes 4u squared times 2 minus u squared, and this becomes 2v squared times 4 minus v squared, and this one is the Jacobian, which is positive. We don't need to put absolute value, dv du. So now let me erase here, then we continue the calculation. Okay, so now we have this integral, right? If I factorize 8 here, so I have 8 times 2 16 the root of 2, so it's here, right? Okay, integral from -1 to 1. Okay, and this one is the same. And look at here left 1 minus u squared minus v squared, right? So let me factorize that minus. So left 1 minus u squared plus v squared dv du. Okay, now we can go ahead and calculate this integral. It's possible, but it's very difficult. Again, look at here, we are going to use another time substitution here. Now here we are in the UV plane, two-dimensional space represented by u and v, and the region is circular. Okay, the region is circular. So to make the calculation easier, we are going to use substitution one more time. This time we are going to use polar coordinate system for our substitution. It means just like x and y, we take u to be r cosine theta, v to be r sine theta. The Jacobian of this substitution is r, and look at here, this is our region, right? To describe it using r and theta, we can say r is from 0 to 1, the radius of this circle, so r is from 0 to 1, and theta is from 0 to 2 pi. So we are going to use this substitution. You will see that the calculation will be much easier. So now we have to put here instead of u and v, and do not forget Jacobian. So let's do it here. I'm going to erase here. Okay, you can see here. So this integral equals 16. Okay, we have this scalar here, 16 the root of 2 from 0 to 2 pi, from 0 to 1. So this is for r, this is for theta. So look at here, 1 minus u squared plus v squared. U squared plus v squared is r squared. Okay, so this is 1 minus r squared. This is the Jacobian. You don't need to put absolute value because r is positive. dr d theta. You can see that the calculation gets much easier here. So now we are going to calculate this integral with respect to r and theta. So I have to erase here. Okay, so let's continue. Here we have, okay, this equals this integral, okay, 1 minus r squared r dr d theta. So this equals 16 the root of 2 integral. Okay, this one r squared minus, okay, sorry, this one r times this r minus r cubed dr d theta. So first we integrate r minus r cubed with respect to r. So you can see here r squared divided by 2 minus r to the power of 4 over 4 from 0 to 1. So the value of this term when r equals 1 minus when r equals 0. When r is 0, this is completely 0, only left when r equals 1. So we can see 1/2 minus 1/4. So the next integral with respect to theta. So 1/2 minus 1/4 equals 1/4, or 1 divided by 4. So it's a scalar, moves out. So here we have. Then left integral from 0 to 2 pi d theta. So 16 divided by 4 is 4. 4 times the root of 2 times, so this one is easy. Integral d theta from 0 to 2 pi is 2 pi. So the product of these two becomes 8 times the root of 2 times pi. So this is the answer to this question, which is the volume of this solid in three-dimensional space. Okay, now look at the next example. We have a triple integral over a bounded region D, which is this solid, a prism. So seems like here the function is f of x y z equals 1. So if we take the triple integral of 1 dv, so this integral means actually the volume of this prism. So as I said, so it means to find the volume of this prism, we have to take the triple integral on d, if you remember here. So if we calculate the triple integral on this d, so we have integral dv. But this dv is the product of dx, dy, dz. But if you remember, I said totally we have 6 possibilities for the order of integration in triple integral. That in this example you can see all possibilities. But let me just explain a few of them. Look at the f, this case f, dz, dy, dx, first with respect to z. So here, first with respect to z, it means we are viewing z as a function of x and y. So look at here. So y plus z equals 1. So actually z equals 1 minus y. So this is upper surface and this is lower surface for z. Okay, so we can say z is from 0 to this plane. What is the equation of this plane? 1 minus y. And then the image of this plane onto xy plane is a rectangle. Is a rectangle. So we can say, you can see here, y from 0 to 1 and x is from 0 to 2, like this. Another order, we may set up this integral in the order of dy, dz, dx. In this order, you are viewing y as a function of z and x, or x and z. So here, look at here. If I take z to the another side, so y equals 1 minus y equals, yes, 1 minus z. So you can see here, here is y 0, right? You can say y is from 0, it means xz plane, to this plane. The equation of this plane is 1 minus z. So you can see, I can say y is from 0 to 1 minus z. It means y is from 0, it means from xz plane to this plane. The plane y equals 1 minus z, you can see. And then you take the image of this this plane onto xz plane. What do you see? A rectangle. A rectangle. So we can say we are talking about this, right? Okay. Because it's dz, we can say z is from 0 to 1. You can see here. And x is from. Okay, sorry for interruption. And x is from 0 to 2. I think here is a typo. This must be x from 0 to 2. So you have to correct it. I'm talking about this. Okay, for y is correct, from 0 to 1 minus z. For z is correct, yes, from 0 to 1. This must be x from 0 to 2. So this is a typo. You fix it. Now look at this. Look at actually this order, dx, dz, dy. Here we are viewing x as a function of y and z. Okay, so look at this, how to say, surface. Okay, here we have a plane x equals 2, which is parallel to zy plane. So if you want to describe, if you view it like like in this way, like viewing this surface as the upper surface, this one as the lower surface. So we can say actually x is from 0 to 2, because this upper surface is a portion of the plane x equals 2, and this is plane x equals 0. So x is from 0 to 2, you can see here. And when you get the image of this surface onto yz plane, you see a triangle. Okay, how do you describe this triangle? Look at this line. The equation of this line is y plus z equals 1. So we can say, so the equation of this line, we can say is z equals 1 minus y. I can say z is from 0 to 1 minus y, you can see here. and y is from 0 to 1. And similarly, you can set up other orders. Okay, so totally we have 6 orders, and the order of the integration depends on how we describe the region. But as I said, we usually try to calculate in this order. Okay, next we have another interesting example. We want to find the volume of this region. What is this region? It's a region between 2 cylinders. Okay, one cylinder with this equation, x squared plus y squared equals 1. This one, which is parallel to z-axis. The other one, x squared plus z squared equals 1, which is parallel to y-axis. Okay, and the region between these 2 cylinders is this one in purple color in the first octane. Okay, so it means we have to calculate the triple integral dv over this region. But how to describe this region to set up our integral? Look at here, we can say for this region the lower surface is z equals 0, is a portion here, the base is a portion of xy plane, means z equals 0. So z is from 0 to here, the upper surface. The upper surface is a portion of this cylinder. Okay, how to find the equation of this upper surface? Okay, using this equation. Look at here, I have done it. I have done here for you. We have x squared plus z squared equals 1, right? So z squared equals 1 minus x squared. So z equals plus minus the root of the square root of 1 minus x squared. So what we are looking for is this, plus. So you can see here. So equation of the upper surface is, you can z equals the root of 1 minus x squared. So you can see z, it means in this order, dz, dy, dx. Z is from 0 to upper surface, the root of 1 minus x squared, this one. Now look at the image of this region onto xy plane. Look at here, the image of this region onto xy plane is a quarter of circle. You can see here this circle here, this circle. Okay, so what is the equation of this circle? Okay, this circle curve is located like, it's like we cut this cylinder by xy plane, so we will see this circle. So the equation of this circle here onto xy plane is x squared plus y squared equals 1. Now we want to describe this base here, this circular base in 2-dimensional space, right? So I can say z is y is from 0 to the circle, so we have to find the equation of this circle such that y is a function of x using this equation that I have done for you. X squared plus y squared equals 1. So y squared equals 1 minus x squared. Y equals plus minus the square root of 1 minus x squared. What we are looking for is positive. So look at this. So we can say y is from 0 to this circle, this one, with this equation. Y is from 0 to the root of 1 minus x squared, this circle. And then look at here, x is from 0 to 1, right? X is from 0 to 1. X is from 0 to 1. So let's calculate the first integral with respect to z. Okay, the integral dz is z. Okay, z from 0 to this. So the answer becomes this one, right? Now look at here, you keep this. The second integral with respect to y, the integral of dy is y from 0 to this. So the answer becomes this minus 0, which is another, the square root of 1 minus x squared. Okay, so now the product of these two becomes how to say, yes, this time this becomes 1 minus x squared. 1 minus x squared. So now when we integrate with respect to x, will be the integral of 1 is x minus the integral of x squared is x cubed divided by 3 from 0 to 1, right? So the answer is 2/3. Remember, we are calculating the volume, and volume cannot be 0. Okay, this is easy. First, with respect to z is z from 0 to this, which is this. Then with respect to y, integral dy is y from 0 to this. So the answer becomes this. So we have the product of these two. And this is 1 minus x squared. The integral of 1 is x. Then minus the integral of x squared is x3 over 3 from 0 to 1. So the answer is 2/3. So remember, this is volume, cannot be negative. Okay, look at here. Next, we have a simple formula. We have a simple definition or formula here. When we say the average value of a function of x, y, z on a region D, this means 1 over the volume of D times the integral of f on D. Please bear in mind this formula. So, for example, we want to find the average value of this function, f of x, y, z. Okay, z is missing here, correct it. Equals x, y, z. We want to find the average value of f on this region D. The region D is cubic. You can see x is from 0 to 2, 0 to 2, 0 to 2. Actually, it's the Cartesian product of 3 closed intervals 0 and 2. So we have to find the volume of D. Okay, D has a regular shape. The volume of this box simply equals 2 times 2 times 2, 8. So this is the volume of D. Now we have to calculate the integral of f on D. So you can see D is a rectangular region. It's a cube. You may set up the order of integration in only any order. Okay, totally remember when you can how to say, okay, here we set up the integral in the order of dx, dy, dz. We are allowed to switch the order of integration if you can describe the region D in other correct forms. Okay, doesn't matter. Here the region is rectangular. You may calculate it in any order, any of 6 order. Let's say in this order, dx, dy, dz. X is from 0 to 2, y is from 0 to 2, also z is from 0 to 2. So the first integral with respect to x. So yz are constant. So the integral of x is x squared divided by 2, yz. X is from 0 to 2. When x is 2, this is 2 squared 4 divided by 2, 2. When x is 0, this is 0. So only left 2yz dy dz. The second integral with respect to y. So the integral of 2y dy is y squared. Sorry, 2y. 2y z dy. Sorry. So z is constant. So integral of 2y becomes y squared z. Z is a constant from 0 to 2. So when y is 2, this is 4. When y is 0, this is 0. So only left 4z. So integral 4z dz from 0 to 2, and the answer to this integral is 2z squared from 0 to 2. When z equals to 2 squared is 4, 2 times 4 equals 8. So now we can find the average value. The average value is 1 over the volume of the volume of D is 8, and the integral of the function on D is 8. So it becomes 8 divided by 8 is 1, right? Volume of D is 8. The integral is also 8. So 1 over 8 times 8 equals 1.